So hello everyone. So today let us discuss one very important topic from magnetism. So that is Ampere Circuital law. So again, you might be thinking, so it's like an simple law where standard questions will be there. So like we are familiar with this concept and this type of like whatever the thoughts that will come to your mind. So it's fine. So but if you really love physics, right? So you just watch till end of this class, and believe me, you're going to love whatever the explanation that I'm going to give here. So for sure you're going to your minds will blow away, because it's like a very beautiful concept where it's not touched in any book, or like standard books, whatever the books that we'll follow. So it might be HC Verma or like DC Pandey or Singhage Galaxy, whatever the book standard books that we'll follow. So and like standard notebooks that even teachers us who will give. So in general we'll miss this point, and it's not an well discussed point. But for sure, okay, if you are a very good aspirant of JE or NEET, whatever it is, for sure I am pretty much sure that at some point of time you would have got this doubt. Okay, so I have got this doubt when I prepared like for JE. And like when I asked my teacher, then he gave some explanation. What is the explanation that he gave, I'll explain. And even when I like started teaching in my starting days of career, so even when student has to, like when student used to ask, like good student used to ask me this doubt. Okay, so when they understand the concept really well, so then they'll get a doubt, like what is the doubt and all that thing, like we'll just discuss in a while. And when they ask me the doubt, even I used to give the answer which my teachers used to which my teacher had given to me, and the same explanation I used to follow. Okay, but somewhere I am not like satisfied with that explanation and all. So like you'll understand what is the reason and all that stuff. But thanks to one of my colleagues, one of my best friends, so PVKR sir, so he like brought me this concept in brought this concept into my notice. And then so complete things make sense for me. Okay, so like I try to explain what is that stuff. Okay, so after knowing this, then your understanding will be better, and for sure you'll love towards physics will increase for sure. Okay, so let us dive into the concept. Okay, so as I said, we're going to discuss Ampere circuital law. So everyone knows like what is Ampere circuital law. If you are like already, as I said, a good aspirant of JE or NEET, so that is closed line integral B bar dot DL bar equal to mu naught into I net. So this is the Ampere circuital law. Okay, so now let us try to understand like this formula here. First of all, what is this I net over here? So in the basic level for the standard questions, all those things you will be having is like you will consider some closed loop, that will call it as Ampere loop, and whatever the net current that is there inside that loop, okay, with the sign convention, we'll consider one direction as positive, another direction as negative, and we are going to get the net current. So that is what we will be thinking the word net means. Okay, but actually it's not. Okay, then what is net current, sir? That we will understand in a while. Okay, but don't think that net current means just when multiple wires are there, I'll just take proper sign convention, and I'll just write like I net is like just like we'll take one direction as positive, another direction as negative, and I'll just add all the currents according to the sign convention. That's what you might be thinking. Okay, but I used to think. Okay, so even I used to think all these things. But somewhere I or not satisfied with the things that I know. But what we can do, within our limits. Okay, I couldn't spend so much of time in figuring out this. But as I said, one of my friends have helped me in finding this, and once this doubt has clear to me, so my love towards physics has increased a bit. Okay, so yeah, so in a while we'll try to discuss about what is I net over here. Okay, and first let us try to understand what is law. So in physics we'll be coming across laws, right? Newton's laws, gravitation laws, Coulomb law, thermodynamics laws, Kepler's laws, whatever that is like. So remember, in physics, whenever we say we discuss any laws, right? So basically laws means they won't be having any proof. Okay, so experimentally they are proven, and so many scientists like try to prove like it is wrong, and so after trying so many times and they when they fail, and like finally those things are like published, and based on that, like we used to like based on those laws, like all those things are designed, and practical things are like working on those things. So basically in simple words, laws means like we does like those things doesn't have any proof. Okay, so only through experimental results those things have come into existence. Okay, and but they're just like in maths, axioms and theorems, right? Theorems are the one which will have proofs, and axioms are the one which doesn't have any proofs, like something like sun rises in the east. So like there is no proof for like sun rises in the east, right? It's just like understanding and just looking at like observing like every day where the sun rises. Okay, so you might be thinking that like every alternative day the direction of the sun, rising of the sun will change. So they observed for like 1 week, it's not changing. Then they thought, okay, at least for 1 month it will change its direction. Then they observed for 1 month, and then for 1 year, and then for 2 years, and then for 10 years, and for 20 years, and for like 50 years. Then finally they like then they came to a conclusion that no, so sun will rise in the east only. So like that doesn't require any proof, right? That's called like axiom. So similarly in physics, laws are the one which doesn't require any proof. Okay, like experimentally they are proven, and we don't have any proofs also for the laws. Okay, so that means whenever we discuss any law in the physics, entire physics, first year and second year together, that means they are true. That's it. Okay, so if something is like when we are applying something and if it is not working, that means we doesn't understand, or like we don't have the clarity to how to use the formula. That's all. But it doesn't mean that like the formula is wrong or the law is wrong. Okay, so we cannot confine the law to like only it will be valid in this case, it won't be valid in this case. We can't confine it like that. So you need to understand that law means that true, always true. If when you apply something and if you are getting contradiction, what does that mean? That means like our understanding of the law is wrong, and like we are applying it wrong. Okay, so for example, like the first question, so here I have asked 2 points here. So in general, okay, what I used to say in my starting days, and like what many teachers they will say, even in books you will find this, that so they'll tell use this Ampere Circuital law either when you have infinite wires or like closed loops. This is a statement that you will find in like many books. Even I used to give my students this concept that use Ampere Circuital law when infinite wires are there and closed loops are there. That means indirectly what I am telling, that means I am telling a steady current should be there. What should be there? A steady current should be there. So that's the like in general the statement that we'll be giving. Use Ampere Circuital law only when infinite wires are there or closed loops are there. But it doesn't make sense. Like its law means it should be always true, right? It's not like only for infinite, only for closed loop. Okay, so yeah, so then for finite it's not valid means, yeah, so by the statement that like teachers has given us, or like yeah, it's true, right? In the books, like whatever they're mentioning, that Ampere Circuital is valid only for like finite wires, like infinite wires and closed loops, or like closed current carrying conductors. So we just take it as granted. Okay, that means this law is only valid under that condition. So it's something like telling like in general years like only in some particular days or only in some particular years only sun rises in the east, right? It's not like that, right? It's an axiom, it's always true. Similarly, if it's a lie, it should be always true, right? And one more point that we'll always say is symmetry is like we will say symmetry is necessary. So the next question, is symmetry like necessary in using Ampere Circuital law? Means you need to understand here one more beautiful concept will be there, that is it necessary means to prove or like to judge whether the law is true or not, the symmetry is not necessary. But to find the value of B, okay, to apply or to judge, to apply ACL, symmetry is not required. Symmetry is not required. So you guys need to understand that like symmetry is not required, okay, for application of Ampere Circuital law, and same goes with Gauss law as well. In electrostatics also we will have closed integral E bar dot ds bar equal to q n by epsilon naught. So there also to apply Gauss law, symmetry is not at all required. Okay, so it's valid for like all the cases. It's need not to be like what the loop that will the Gaussian surface that will consider there and the Ampere loop that will consider here. It's need not to be a like what symmetrical one. It can be anything. But to find the value of b to find the value of b mathematically the Ampere loop AL, I am calling it as Ampere loop AL, must be symmetrical. So why? Because if it is not symmetrical, if it is some random shape like this for this current carrying conductor, then I don't know the maths how to solve it. Okay, we don't have like mathematical abilities or like for random things. Okay, we don't have like that much mathematical capabilities or abilities to solve the integral b bar or dl bar if the angle is continuously changing and we don't know how the angle between b bar and dl bar is changing. So basically we cannot do the mathematical calculation if the loop is not symmetrical. So that is the only reason to find the value of b. Sir, is the Ampere circuital law valid only for symmetrical case? No, it's like valid for any case. But if you want to find the value of b by using Ampere circuital law, then the loop that you need to consider it should be what? For sure it should be a symmetrical loop. Okay, why? Because as I said, like if it is not a symmetrical loop, then you are not able to do maths for that, and you are not able to get the value of b. So that's the reason it should be symmetrical. So I understood. Okay, like why it should be symmetrical. So as I said, if it is unsymmetrical, then we don't know the maths. Okay, like we don't know the maths behind that. Like how it will get solved, so it will be very difficult and you cannot do the maths behind that. Okay, but if it is symmetrical, then you will be able to do the mathematics behind that and you can find the b. And same goes with the like electrostatics Gauss law as well. Okay, yeah. So now let us take some 3 different cases just to jump into this whatever the analysis that I want to do. So to discuss that concept, I have taken 3 cases over here. Sir, what are the 3 cases? In the case 1, I have taken pretty much the standard one. So I have taken an infinite wire. From Biot-Savart's law, you know the formula for this one is what? Mu naught I by 2 pi d. Sir, how you know the formula? Mu naught I by 4 pi d into sin theta 1 plus sin theta 2. And for Biot-Savart's law, it will be the angle becomes 90 and 90. And you will be getting mu naught I by 2 pi d. You know the formula. Okay. But I am going to derive that formula by using Ampere circuital law. So I have taken an infinite wire and I consider an Ampere loop over here which is completely symmetrical with respect to the wire. That means every point of this ring or like Ampere loop that I have considered is at a distance of r. And we know around the wire straight current carrying conductor we will be having what? So circular magnetic field lines will be there like circular loops. So that means magnetic field is also circular and the Ampere loop that I consider is also circular. That means B bar and DL bar are in same direction. So B bar and DL bar will be like basically they will be tangential. Both will be in tangential direction. B bar is also tangential and DL bar is also tangential. That means angle between them is like what? Fixed. Always angle between them is always 0. Then I can remove this dot product and I can simply write it as what? Integral BDL, because cos 0 will be what? 1. So other than the circle and symmetry, if you take, sir, I will take a square. Then when you take a square, the distance will vary, the angle between B bar and DL bar will vary. So it's like we cannot do maths in that. Okay, it's like way too much stuff, and within the mathematical boundaries that we have, limitations that we have, we cannot calculate that. But whether it is true or not, yeah, it's true. It's obviously true, but we cannot deduce the value of what? B. Okay, so then as I said, as B bar is also tangential and DL bar is also tangential, angle between B bar and DL bar will be 0. So when you do dot product, so cos 0 will be 1. So simply I will get integral BDL. But one more important thing. What is one more important thing? The one more importance of taking symmetrical points is, as all the points are symmetrical, B is same everywhere. So as B is same everywhere, what I can do? I can take the B outside. That's one more importance of like taking a symmetrical loop. When you take symmetrical, B everywhere is same. So we know constants can be brought outside, whether it is in case of differentiation or integration. So whether it is a case of integration or differentiation, I can bring the constant outside. So as b is constant, I'll take b outside. Then what will be left? They will be left out with integral dl. So integral dl means adding all those small lengths. So what is sum of all the like integral dls? So you'll be getting total length. Total length is nothing but what? 2 pi r. So b into 2 pi r equal to mu naught into I net is there is only one current carrying conductor. So I just took that I. So I got b equal to mu naught I by 2 pi r. Yeah, sir. Yeah. So everything is fine. So already you know, sir, from Biot-Savart's law also we know the formula. So b should be mu naught I by 2 pi r. And here also by using Ampere Circuital law also I got mu naught I by 2 pi r. Yeah. So till here, so there is no like contradiction or no ambiguity. So it's everything is fine. So now let us jump into the like main case. So that is case 2. So now when I go to case 2, here I took a finite wire. Earlier I took an infinite wire. Okay. Now I took a finite wire which has a length of what? 2r. Okay, so I took a wire which is of length what? 2r, and I consider a loop which is completely symmetrical to that wire. So each and every point of that loop is at a distance r, and above that loop there is an r length of wire, and below that loop also there is an r length of wire. So obviously it is symmetrical. Yes sir, true. And but okay, I haven't taken it as an infinite wire, or it's neither a closed loop or it's not an infinite wire. Okay. So but like we'll say, like in general books we'll find that it should be either infinite or closed loop, then only we can use Ampere Circuital law. Okay, why they'll be saying like that? Okay, we'll understand in a while. So again I did the same process, closed integral b bar or dl bar. Again b bar will be circular. Okay, and angle between b bar and dl bar will be 0, so you'll get b dl. Again, as it is symmetrical, b is same everywhere, so I can take b outside, and b integral dl is nothing but what? Again, length of the total loop, which is nothing but 2 pi r. So b into 2 pi r equal to again mu naught into I net inside. What is the current inside? Current inside is I itself. So mu naught into I. So I got b equal to mu naught I by 2 pi r. Okay, but you know that. So b is not mu naught I by 2 pi r. So mu naught, like for this case. Okay, sir, how we know that it's not mu naught I by 2 pi r? So how we know this means I have just derived this for like formula for this by using Biot-Savart's law. So remember, Biot-Savart's, it's also an law, Biot-Savart's law. Okay, so there is like what? No need of proving it again or something. Okay, so it's a law. So by using that law, we have derived a formula for what is the magnetic field due to a straight current carrying conductor, circular current carrying conductor, and arc, and all these formulas we have derived just by again taking Biot-Savart's law. So it's also law. So it should also be always true. So sir, I have used Biot-Savart's law and I got this value. Sir, I used Ampere Circuital law and I got this value. Then here we got an ambiguity. By using Biot-Savart's law, I got mu naught I by 2 root 2 pi r, and by using Ampere Circuital law, I got mu naught I by 2 pi r. So like where we have went wrong. So both are laws. Okay, both should be correct. Okay, it's not like sir in this case it should be right, in this case it's not right. So we cannot say like that. It's law means it's always true within the limits. Okay, what are the like limits that are there? So but again then like in general books and like we like even when I don't know, I used to come up with this note point that okay, we are just constrained and like we are dealing with a particular special case. That's it. I'll pass a statement that use it either we have an infinite wires or like closed loops. We pass a statement and then we'll say, sir, here you have taken a finite wire, so this is wrong. So because you cannot use Ampere Circuital law when finite wires are there. So but Biot-Savart's law is always, it can be used always. So I have derived the formula. In the derivation everything is there. So that's why this formula is right and this is wrong. Okay. So here there is a takeaway here. The thing is, Ampere Circuital law is not wrong. Okay, it's a law. It should be correct. And so what happened in this case? Why can't we apply for the finite case? Because we don't know how to apply that formula. As I said, whenever there is no way that laws can be wrong. Okay, laws are always true. If it is wrong, that means you don't know how to apply it. Okay, but that means you are not completely like in hold, or like you are not having complete clarity of that concept or that formula. So that's what happened here. and by doing this we'll say no, Ampere circuit law is valid only for like infinite wires and closed loops. No, it's a lie, it should be true always. Okay, then what happened here? What happened means here the understanding of inet comes. The starting of the class I told, so understanding of inet is very very important. So as I said earlier, what we used to think, or like what everyone will think, inet means net current, like whatever the currents that are there in the ampere loop, that's what they will think. Yeah, it's like basically whatever the currents that you're thinking, that's like conduction currents. Okay, but actually speaking, okay, the actual Ampere circuital law formula is this. Actual Ampere circuital law formula is, as I said, you won't be able to find in like the standard books this one. Okay, like in very good books or like foreign other books only you will be able to find this. So integral b bar dot dl bar, I guess it's there in HC or no also, I am not sure. Okay, but this explanation part is not there. You might find the formula somewhere. Okay, but whatever the explanation that I am going to tell, okay, so I haven't seen it like in any books. Okay, so as I said, my friend has found it in like some foreign author's book. Yeah, so integral b bar dot dl bar equal mu naught into I net, where I net is what? I conduction current plus displacement current. So again, like you will be completely blown away. Like so, EM waves concept of like displacement current has come here. See, so it's like basically it's a physics, right? So we have divided this into like different chapters and we are studying it separately. But actually speaking, it's like completely physics, and I can have link between any topics. Okay, it's not like sir, like it's magnetism chapter, EM waves is a separate chapter. We have divided. It's completely actually it's a physics. And like when Ampere has given this formula, okay, when this law has like been proposed, so he has given that like I net is not just conduction current, I net should be like conduction current plus displacement current. That's what he has said. Then you will be thinking, sir, like what is displacement current? Like why displacement current is coming over here? Why? Because when finite current is like there, okay, when finite wire is there, so then see here, if you observe, I have shown current I. Then you should be asking or thinking, how come a finite wire can carry a current I? If it is a closed loop, yeah, obviously it can carry a current I, it's continuously that will circulate. And infinite wire, then again you might be thinking, sir, then in infinite wire also how can current can carry? In infinite wire, I can assume a loop which is at infinite, which doesn't have any effect on the loop. Ampere loop that I have taken, as the wire is already infinite, I'll close it and I'll make it a loop. And sir, then sir, like how can you add sir random things to make it loop? Then sir, here also I'll add it and make it a loop. No, when you make it loop here, then you need to understand that these things are going to affect the magnetic field over here. That I cannot do. Okay, but when it is infinite, when I am considering the loop at the infinite, so tell me, will those wires, will they be having any effect over here, the loop that I am considering? No. So that's why you need to understand, even in the case of infinite wires, they are closed loops. That means, as I said, the starting point, the steady current can be seen either in infinite wires or like closed loops. But when finite wires are there, how can you see the like steady current? You cannot see the steady current. Who is the source for that current then? Like there should be some source for the current, right? How come the current I can flow simply in the air? Cannot flow. So like sir, then what should we do? So to justify it, okay, when I say some current I is flowing, to justify it, what I am telling means, assume that here Q charge is there, here minus Q charge is there. Assume here Q charge is there, here minus Q charge is there. Slowly this charge will discharge from here to here. Let's say from here dQ charge will be like lost and the dQ charge will go over here. Slowly this charge is discharging from Q to minus Q. The charge is going from like positive this point, B point to A point, and because of that the current is like flowing. Now it is justified. That why current is flowing. That means clearly you can see that like what is the cause for that current. But now because of this charge, whenever charge is there, like obviously electric field will be there. Okay, because of this minus Q also electric field will be there towards it, and because of this plus Q also electric field will be there, right? So now as because of both the charges electric field is there, okay, because of both the charges electric field is there, so because of the flux will be developed. So flux through what, sir? Flux through whatever the surface that I've taken, the ampere loop that I've taken, or the surface that I consider, through that the flux will be changed. And we know whenever flux is getting changed, then displacement current will be there, right? That's what we'll be learning in EMFs, right? The displacement current is nothing but what? Epsilon naught d phi E by dt, correct? So even Ampere Circuital is valid for like finite wires also, like even for finite wires also Ampere Circuital is valid, but only thing is we need to apply it correct by taking this formula. Now let us try to like calculate the value and check whether we are getting the same value what we have got in Biot-Savart's law or not. Okay, so let us check. As I said, mu naught into I net means in the I net we will be having both conduction current as well as displacement current. This is conduction current and this is what? Displacement current. So conduction current already I know, which is nothing but I, which is minus dq by dt. So why minus dq by dt? Why? Because the charge is flowing from here to here, the charge is decreasing, right? So that's why the rate of like here charge is getting decreased, so that's why here minus should be there. So minus dq by dt. Then sir, what is the formula for displacement current? Displacement current formula is what? Epsilon naught d phi E by dt. Epsilon naught d phi E by dt. Phi is electrical flux. Now to find this displacement current, first of all I need to find electrical flux. So let us find what is electrical flux over here. So electrical flux is nothing but, so whatever the flux that will be there because of positive charge, okay, just like mirror image, the same amount of flux will pass through this whatever the ampere loop that I have taken. So I'll just find what is the flux due to positive charge Q and I'll multiply it with what? 2. Okay, so 2 into like whatever the flux due to only one charge. So what is the flux due to a point charge? Okay, so you know like it's a standard formula, q by 2 epsilon naught into 1 minus cos theta, right? So when you consider a cone, the amount of flux that will be going is like what? Q by 2 epsilon into 1 minus cos theta, where theta is the semi-vertical angle, right? For the cone, whatever the semi-vertical angle will be there, that angle we need to consider. So I just use that formula, q by 2 epsilon into 1 minus cos theta, the semi-vertical angle is 45 degrees. Why? Because as I said, the question that I have taken, this length is also r, this length is also r. Sir, is it valid for only the equal lengths? No, whatever might be the length, you just need to find this angle. Okay, it can be any length, okay. So I just took a special case over here, but don't think that it's valid only for special case. Whatever the case that you want, you can consider it, okay. The only thing is you need to get this angle, semi-vertical angle, then I can use this formula. Then displacement current is nothing but what? Epsilon naught multiplied by differentiating this. When you differentiate this, so this constant can be kept outside and dq by dt will be there. So I just did epsilon naught d phi E by dt. So in this, what are the constants here? Like 2 anyway got cancelled. Epsilon naught and this entire thing is constant. I just simplified over here and yeah, so epsilon multiply and just dq by dt will be there because q is a variable thing. And now from here, dq by dt is nothing but what? When I is minus dq by dt is nothing but minus I. So that I just substitute over here. Then I net current is nothing but, this is conduction current plus this is displacement current, right? Now in displacement current, in place of dq by dt, I am replacing dq by dt with what? Minus I. So this is conduction current and this is displacement current. So net current is nothing but what now? Conduction current plus displacement current. Now you can see that this is the net current that I am getting. How much? What is the value of net current I am getting? The net current that I am getting is I by root 2. Net current that I am getting is what? I by root 2. So here, as I want to find the B value, obviously I need to take what? Symmetrical loop. So I consider symmetrical loop. So it's a finite wire. How can you apply Ampere Circuital? Yeah, I can apply Ampere Circuital. It's a law, so it's true for every case. Yeah, but the way that we apply till now, the thought process that we have till now, it's like wrong. Okay, so I have just recorrected this. Now after knowing this point, we can apply it. Now I got to know what is the I net current. Okay, it's not just like conduction current. Along with the conduction current, we should have displacement current also. But when steady state currents are there, then there is no point of displacement current. Okay, when steady state charges are there, then there is no point of like displacement current. Only in case of like what this type of cases where there is like no particular source for the current, then here like there is a need of like what, telling the cause of that current. So for that cause we have replaced this q and minus q, because of which the flux is changing. Whenever the flux is changing, obviously the induced electric field will be like produced, right? So then I got the I net, and as I said, to calculate the value of B, I need to take what? I need to take the symmetrical loop. So I have considered the symmetrical loop over here. Then again the B will be like what? B will be like circular. Okay, B will be like circular around that, and DL bar is also what? Circular around that. So then again angle between them, whatever I have done in the three cases, the same thing over here. So angle between B bar and DL will be 0. So then cos 0 is 1. So B is it's like B is symmetrical for everything. I can take B outside, and B integral, again DL bar is nothing but sum of all these lengths, which is nothing but what? 2 pi r. So B into 2 pi r equal to mu naught into I net is not I. I net is not I. Just now I calculate the entire thing. I net should be what? I conduction plus I displacement. Okay, so I just substituted over here. The I net is I by root 2, and I got this value. Just let us check this, okay, whether it is the same value that we got with Biot-Savart's law or not. Yeah, it's true. So mu naught I by what? 2 root 2 pi r, and you can see that here also I got what? Mu naught I by 2 root 2 pi r, right? So like I hope now it does make sense, right? Like whatever the perceptions that we have till now about Ampere circuital law, okay, I guess this is like one of the biggest misconceptions that I used to have when I am a like student. Even as I said, in the starting days of my like teaching career, okay, not starting days, even till like last 5 months, I came to know about this like concept just 5-6 months back. So till then, even I used to think that Ampere circuital is valid only for like Ampere circuital is valid only for like what infinite wires and closed loops where steady current will be there. Okay, but I guess like your complete perception or like complete misconception has got cleared, and we have clearly observed here that okay, so even with the help of like Ampere circuital, you can get the value for a what? Finite wire. Okay, it's not that we cannot get magnetic field due to, like of a finite wire, magnetic field due to a finite wire by using Ampere circuital. No, but sir, is it lengthy and difficult? Yeah, it's lengthy and difficult. So instead of that, I would be like using what? Biot-Savart's law, because I know the formula for straight current carrying conductor, right? But as I said, it's like good to know, like good to clear whatever the misconceptions that like what we'll be having in physics subject. Okay, so like I felt very happy after knowing this point. Okay, so obviously as a physics lover, so whenever I get to do a good question or like get to know some good concept, okay, by solving some good questions, so obviously like so that entire day it will be like full of happiness. Even now I was like so happy sharing this point to everyone, because I don't have this like what source, or like I don't know all these points when I used to study, even when I used to teach, right? So I thought it would be very nice if I share the point that I know. Okay, so like this there are many like beautiful points that I can share. Okay, similar to this, one more important point is like electric field E equal to like Ohm's law will say E equal to like rho J. So in that, what is the E there? Okay, what is the electric field? Again we'll say net electric field. What is the net electric field there? Okay, so like there are like many beautiful points. Okay, so slowly I'll try to cover each point and like all the concepts. Okay, so we'll try to like I'll try to get some good content where like more like your misconceptions can be cleared, or like the areas where okay people will be feeling difficulty in understanding. Okay, so obviously, so your love towards physics will increase when you find these type of points only, right? So if you love physics, like if you have a passion, like what, so much interest towards physics, then obviously would have loved this point. Because if I would have known this point when I used to study, right, then I would have like felt so happy. Okay, because even though when I'm not a student, after knowing this point, I was like so happy. I can't even express how happy I am like after knowing this point. Even till date, I was so happy that like most of them doesn't know this point, and I came to know that point, right? That's like satisfaction that we'll be having, right? So, but I just wanted to share this point to everyone so that everyone will be like thorough with this concept, and they won't be having any misconception regarding this. So that's what like my intention. Okay, so I hope you like the explanation over here for this concept. Okay, yeah. Okay then, thank you. Bye bye.